Hey guys, welcome back to another video. In this video, we're going to be talking about electric potential energy. In the previous video, we talked about electric field strength, which was basically force per unit charge, the amount of force exerted by the electric field of a certain charge at different distances, be it here, 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 or here. Right, so that is electric field strength, the strength of the field at different positions, and that is measured in terms of force. And this was the formula that we derived. Right, so right now we're going to be talking about energy, and this energy is actually closely related to the force. How? Because for a force to be exerted on a particle, on an object, if that object moves a distance, force into distance is work done. So similarly, a similar logic is applied over here, but it is in terms of charges, right? In case of charge, we express that energy as electric potential energy. The work done is expressed as electric potential energy. Work done in the sense that amount of work done on the charge or by the charge in moving it from infinity to a certain point. Now, this definition might seem similar to that of gravitational potential energy, and that is because it is similar. The logic is quite similar, but I need to clarify one basic thing about the difference between gravitational potential energy and electric potential energy. Mind you, for gravitational forces, right? Let's say this is your Earth, our green Earth, and the gravitational force, the fields are actually always attractive. Therefore, if there is another small planet, let's name this planet B, planet B will always be attracted towards Earth, and this Earth is going to be attracted towards planet B. So in that sense, we know that the electric potential energy is actually always negative. Why? Because the field lines are always inwards. The field lines are always inwards, meaning they are attractive forces. If there is any object placed over here, this will feel a force that is towards the center of the Earth. And these are, as I said, attractive forces. However, with charges, by the way, it's a bit different. There can be repulsive force and there can be attractive forces. So if you already know a small key to this, that is, attractive forces always give you negative potential energy and repulsive forces always give you positive potential energy. If you don't know, that's fine, but that is a short way to remember what's happening in case of charges. If there are two positive charges, what's going to happen is these are going to be repelled, right? And if you, let's say, bring this charge from this point, from let's say infinity to point A, you have done positive work on the positive charge. Therefore the charge has actually gained potential energy. In this case, that energy is positive. However, if this was a negative charge, what would have happened is bringing it from infinity to this point would have been negative electric potential energy. Negative work would have been done. In case of gravitational fields, it's always negative. It's never positive. So that is the clear distinction between electric potential energy and gravitational potential energy, and in a lot of questions they're going to ask you that. So yeah, I'll step by step go through what is electric potential energy, why is it ever negative, why is it ever positive, why do we, how do we decide the sign of the electric potential energy? And yeah, let's start off with the definition of electric potential energy. We denote it as U. Alright, so electric potential energy is the work done in bringing a charge from infinity to a defined point in electric field. Okay, what does that mean? Similar to that of gravitational fields, you know gravitational potential energy as the amount of work done on a point mass to bring it from infinity to a defined point. In case of charges, what's happening is you remove the mass and bring in a charge, and in this case you're talking about any charge, be it q1, q2, any amount of charge. Electric potential energy is talking about, let's say, be it 5 coulomb, 10 coulomb, or 15 coulomb. What is the work done that will be done on the charge in bringing it from a point infinity to a defined point, let's say r? Gravitational potential energy is giving you that work done. So now coming back to the point of positive and negative, how we decide why it's positive and why it's negative, I'll go through it shortly. I'll be explaining this in gravitational fields as well, but I'll explain this over here as well. Okay, so before going into the derivation of electric potential energy, in short, let me tell you, if let's say this is a negative charge, right? This is a negative charge, and it's going near a positive charge. Okay, are these attractive forces? Yes, they are. They are attractive forces. And now you place this charge at infinity. You place this charge at infinity, where the force will be 0. The force on minus charge is 0 at infinity. Why? Because at infinity, the field strength of charge q has become 0. It's so negligible that it's 0. So since there is no field strength of this positive charge at infinity, the force applied on q2 is 0. However, if you bring q2 near q1, what's going to happen is you're not doing any work on the charge. This field itself is pulling q2 towards it. Agreed? Okay, great. Therefore, as it comes closer to q1, q2 loses its energy from 0 to a negative value. Why? I'll explain it in a moment. So let's say at infinity the force is 0, so its potential energy is also 0. Since it's not feeling any tug, right? Its potential energy is 0 at infinity. So why is it becoming negative, being an attractive force, when it comes closer to q1? Why is it becoming negative, right? The reason is, let's say q2 is placed over here, right? q2 is placed over here. Now imagine you have to move q2 from this point to infinity. So we are going in reverse right now. We are moving the charge from point A, let's say, let's take it to R. So let's say from R we are moving it to infinity. At R, its potential is going to be negative. Why negative? Because from R to infinity, you're going to do work against the field of q1. Against the field of q1. Why? q1 is trying to attract the negative charge towards itself. However, you are trying to move the negative charge in the opposite direction. You're trying to move the negative charge in the opposite direction, which is why you're doing work on this negative charge. in trying to move it away from the positive charge, which is attracting it. Good. So if you're putting in your work inside the charge, to the charge, where is the work then going? From your hand, let's say I'm trying to move this bottle from this point to this point. Where is my work then going? Where is my energy going? So that energy actually converts to potential energy inside the charge. But, if that is what's happening, then from R, pushing it away to infinity, shouldn't it become something of a more positive value? Because you're doing work on it, so it should become something more positive. Let's say at this point, the potential energy was 5 joules. And from this point, you're doing work on this, and you're pushing it away to infinity. So it should become something like 100 joules now. However, that does not happen. Why? Because initially we established that at infinity, your electric field is non-existent. So the electric potential energy of the charge at infinity is actually 0. So how does it increase to 0? The only explanation to that is near charge Q1, its potential energy needs to be negative. Its potential energy over here near the charge Q1 needs to be negative, because otherwise it cannot increase to 0. You are putting your energy into the charge. So where is the energy going? It is converting into potential energy and increasing to 0 from a very negative value near the charge. That is what we express in this curve. So in this curve, I've plotted the force and the distance. Near charge, it's feeling a greater force, maximum amount of force near the charge. And as it goes away, the force decreases. And at infinity, you'll notice it is 0. The force is 0. So if you're pushing this negative charge Q1 from this position to this, you have done work on it. And that work has converted into potential energy of Q2. And the potential energy of Q2 from this position to this position to this position increases to 0. That is why for attractive forces, the electric potential energy is always negative. Because whenever it is in the vicinity of another attractive charge, in this case a positive charge, your electric potential energy has to be negative. Otherwise, it cannot increase to 0 at infinity. Now that is one explanation for why electric potential energy of attractive forces is always negative. Quite conversely, for opposing forces, what's going to happen is these are going to repel each other, right? And at infinity, no such potential energy, because it's not in any contact of electric field, because its electric field is going to decrease to 0, right? At infinity again it's 0. However, what you're going to notice is at infinity, if the field is 0, E field, why am I writing with this? Okay, the E field at infinity is 0, force is 0, therefore your potential energy is EPE, electric potential energy is 0 at infinity. However, if you have to push this positive charge to, let's say, R, you have to do work on the charge. This is not going to attract the charge. Now you have to put in energy. You have to give it energy from infinity to R. You are doing work on the charge, because these are going to be repulsive forces, and these charges want to move away from each other. So from 0 it increases to, let's say, 100, then increases to, let's say, 200 joules. So therefore, for repulsive forces, what's happening is at infinity it's zero and it increases as it comes closer to the repulsive charge, right? That's why for repulsive forces, the electric potential energy or potential energy is actually positive. So that is the main clarification that I wanted to go through before I delve into the derivation. I hope I could have cleared out the confusion between attractive forces and repulsive forces and why electric potential is negative or positive, right? Okay. So from this, if I want to go back to deriving electric potential energy, notice electric potential energy again is the amount of energy needed to bring a point charge from infinity to a defined point, let's say in this case r. Okay, so this highlighted portion is the work done. How is it the work done? Remember, work done is nothing but force times distance. On this axis you have the force exerted by q1, and on this axis you have the distance covered from infinity, right? Therefore, if you integrate from r to infinity, you should be getting the work done. You should be getting the work done. Great. So by integrating the force and distance curve, you will figure out the work done on the charge, which is going to be your electric potential energy. Great. So we can now directly move on to the derivation. You don't need the derivation. You can just completely memorize the formula for electric potential energy, so you can skip to the end of this derivation if you don't want to see all this, but some of you might be interested, so I'm going to show the derivation. Okay, so proving the formula for electric potential energy. Electric potential energy defined by U is equals to the negative of integral of force with respect to what? R. Why? On the x-axis we have R, and what are we integrating? The force from R to infinity. So the bounds are R and infinity. We are starting off at infinity, ending at R. Agreed? Good. So upper bound R and lower bound infinity. Great. Why the negative charge? So for the negative charge, what's happening is, let's say initially we were talking about like charges, but if you're talking about, let's say, repulsive charges, let's say positive, positive, negative, negative, in case of that, then the force, notice, is opposite to the direction of the movement. What does that mean? So let's say for dr, this is the, distance is with respect to, let's say, in this direction, and the force applied is actually in this direction. What I mean by that is, if you notice in this example of, let's say, a positive charge and a positive charge, what's going to happen is, if you're moving this positive charge from A to B, the force exerted on the positive charge is not in this direction. It is not in this direction. It is rather in the opposite direction because of the repulsive force. However, the movement is from A to B though. The movement of the particle charge is from A to B, because you're doing the work done. You're pushing the charge from A to B. So the movement is from A to B. However, the force by this is being exerted rightwards. So notice that your direction of force is opposite to the direction of movement, and that is why we use the negative sign. Anyways, so again, the bounds are from infinity to R, and the constant k, if you remember from the last video, 1/4 pi epsilon naught. So that is your constant. You keep the constant as it is. The other variables which are constant are q1 and q2. because q1 and the charges are not going to vary with distances, right? So you can plug it out of the integral, right? Take it out of the integral and you keep it outside. Since these are constant, you can do that. Okay, so inside what do we have? We have, look at this step, upper bound r, lower bound infinity, and inside we have 1 by r squared, and we are going to integrate with respect to what? The distance, the separation. Great. So now what you do is you're going to basically simply integrate it without any hassle. So if it is r to the power minus 2, how do you integrate it? R to the minus 2 becomes r to the minus 2 plus 1 divided by minus 2 plus 1, and it's going to become 1 by r minus 1 by r, right? So this is what it becomes, right, after integration. Okay, so if you have integrated it, now you have the bounds to be plugged in, right? So what do? You plug in the upper bound over here, and then you plug in the lower bound over here. Good. So if you do that, r 1 by r minus this lower bound, which is 1 by infinity, and what you're going to be left with is, since 1 by infinity is actually 0, 1 by infinity is 0, since 1 by infinity approaches 0, therefore you can express it as 0 over here. So minus 1 by r minus 0, which is minus 1 by r, and if you know that the minus and minus now is going to be cancelled out. So what you're left with at the end of the day is gravitational potential, electric potential energy is K, the constant, times the product of both the charge divided by the separation. Okay, so I know this is very similar to the force formula, which is K q1 q2 by r squared. So just remember this as removing the square from the separation, and then you have the formula for electric potential energy. Okay, so that is your formula and how we derive the formula for electric potential energy, right? Okay, so in this case, notice the reason we took the minus over here is actually helpful. Why? Because let's say you have a positive charge and a positive charge over here. Since we have initially already considered the negative charge, now if you have two positive charges and you plug both the positive charges, your ultimate GPE value is going to be positive, because positive times positive is positive, constant is never negative, so positive divided by a positive value, which is the separation. So ultimately you get a positive gravitational potential energy, electric potential energy value. So you get a positive electric potential energy value, and you know from the explanation before that if there are repulsive forces, the electric potential energy is always going to be positive, right? And in case of, notice, a positive and negative charge where there is attractive force, if you plug in negative over here, positive over here, what's going to happen is the negative and positive is going to give you ultimately a negative answer, and that matches with our scenario where you have a positive charge and a negative charge interacting. They are going to be attracted, therefore their electric potential energy is going to be ultimately negative, and by the formula we do get that. That is why it was important to have this negative sign in front of the integral. Okay, so hopefully I could explain the derivation. I guess there is a bit more to it. Wait. Okay, so let's now talk about the change in electric potential energy. Previously we just learned about the electric potential energy, which is from infinity to a defined point, let's say r, right? Now we are going to talking about how to find the change in electric potential energy from any position, let's say A, to another position B. Okay, so it can be from here to here or here to here, doesn't matter. We have to find out the change in potential energy. Okay, and in that case what we do is, the main idea over there is you have to integrate from, let's say, point A to point B. How do you do that? Just like before, you introduce bounds In the previous case it was infinity and r, because we were talking in terms of from infinity to r. Right now it's going to be from any position a to any position b, or the other way around. All right, so let's see how to find out the formula, and it's derive the formula for change in electric potential energy. Good. So we have again a charge q1, a charge q2, and over here we're going to see the interaction between both of these charges, and we're going to move, let's say, q2 from this position to the new position r2. Okay, so to find the change in electric potential energy, again we integrate this curve from position 1 to position 2, and you're going to integrate and find out the work done on the charge q2. Okay, so in this case they can be repulsive, they can be attractive, you don't know that. Moreover, you don't know if the charge is moving from r2 to r1 or r1 to r2. You don't know that. So that is why we don't introduce a minus sign over here, because it can be both negative or positive. The force can act in the direction of the movement, or it can act opposite. You don't know that, and it's going to depend largely on what is your r1 and what is your r2. That is why we don't have a minus sign over here, but previously we did, because we know we were working with from infinity to a point closer to the charge, that is r, or any such point near q1. Okay, so over here we don't introduce the negative sign over here, and let's move on with the exact same process of integration. Okay, so in this case, let's say we're moving from position r1 to position r2. What is electric change in electric potential energy? Very simple. You integrate from r1 to r2. Okay, so in this case, since you're moving from r1 to r2, you're going further away. Great. So this is your force, of course, and you're going to integrate with respect to the radius. Okay, so again you take the constant out of the integral sign and you're left with integrating this. Okay, so how do you do that? Again, 1 by r to the power minus 2, it's going to turn into r to the power minus 2 plus 1 divided by minus 2 plus 1, and that's going to give you in return minus 1 by r. Do we have minus 1 by r? Yes, we do. Great. Okay, so now what do you do? You're going to plug in the bounds into the variable over here, and you're going to see, if we plug in, let's say, r2, we're going to have minus 1 by r2, then again the minus sign, because you minus the lower bound from the upper bound. Okay, good. So now we plug in this entire thing over here, and we're going to put in r1, so 1 by r1, and you're going to be left with minus and minus. That's going to turn into positive. So you typically over here have minus 1 by r2 plus 1 by r1. So in this last step, what I have basically done is change the position of the r1 and r2. Okay, so if you do that, you're going to be left with r1 minus r2. Now in this case, mind you, r1 can be the any of the initial position, right? You can consider this as r1, you can consider this as r1 as well. It doesn't really matter. Why it doesn't matter? Because depending on from where you're moving to where, your sign is going to vary accordingly. I'll give you an example over here. So let's say we are seeing an interaction between two positive charges. Okay, we're seeing the interaction between two positive charges. And in that case, if I'm moving away from the charge, mind you, it is losing its energy. Why? Because near the positive charge, remember, repulsive force, the electric potential energy is more positive. As you move away from the positive charge, it's going to reach 0. It's going to decrease and reach 0. Okay, great. So if we are moving away from R1 to R2, in this case, R1, since R1 is the bigger number, why? Because we are counting from origin to R1. R1 is the smaller number, right? R1 is the smaller value, and since r1 is the smaller value, the reciprocal of it is going to be the bigger value. And the opposite for this is r2. Since it's more it's away from the origin or your initial charge, it's going to r2 is going to be larger. Okay, so larger, but the inverse is going to be smaller. Okay, so in that case what's going to happen is your final answer is going to be a positive value. However, that is your change. This value that you get after subtracting both of these and multiplying the entire thing and getting the answer, you're going to see your final answer is actually positive. But do not worry about the sign. Why? Because in that case they're talking about the change, right? The change can be positive or negative, and you should be understanding that if it is positive, it's going to be coming towards the positive charge. But in this case it's moving away. Since it is moving away from the charge, the change is actually negative. It is a negative change. So when you're writing your final answer, you can write it as minus the value you get from this equation. Okay, so the change can be both positive or negative. You have to read the question and see what is happening. If the positive charge is moving away from the positive charge, it's a negative change. The electric potential energy decreases. Again, if the positive charge is coming towards or coming closer to the other positive charge, in that case the change is actually positive, since the electric potential energy is increasing. So read the question, understand what is happening, if it is moving away, if they are repulsive charges, if they are attractive charges, and keeping that in mind, you can write the final answer as positive or a negative change. Okay, great. So this is how you find out the change in electric potential energy. This is your final equation. This is your constant in this case, because the charges are not going to change, and this is your variable, and you just plug in the distances and you're going to find the change. Okay, great. What do we have next? What does having a positive or negative electric potential energy value mean? Right, so if you have a positive electric potential energy, mind you, positive electric potential energy, not change. So yeah, if you have positive electric potential energy, work is done by an external force on an electric field. We get this since both Q1 and Q2 have to be like charges for you to be positive. If they are like charges, they repel each other. Since they repel, an external force needs to work to bring them closer together, as explained above and previously. When you have two positive charges, they're going to repel. Until and unless you exert an external force, they're not going to come closer together. In that case, positive work is done. That is why your EPE, since coming from infinity to a defined point, is positive. Great. When EP is negative, what's happening is work is done by the electric field. Remember, I talked about the charge of this field attracting this charge. Yes, that is what they mean by, I mean by work is done by electric field on particle. Right, since electric potential energy is a negative, that means Q1 and Q2 are opposite charges. Therefore, they attract each other, so the electric field is enough to bring them closer. Great. So this is the basic summary of what we were talking about, and how the charges interact, how the electric potential energy works, why is it positive, why is it negative. Hopefully, after all this, you understand what is the significance and why we have a negative sign in front of electric potential energy in case of attractive forces. All right, that is it for electric potential energy. Next video we talk about electric potential, which is basically the same thing but only for unit charges. All right, see you in the next video.